एकच मिनिट, अजून माईक कुणी कुणी बंद केलेले आहेत आपल्यातले.
खरात सर, माने सर बरं का.
गायकवाड सर नमस्कार.
खरात सर, माने सर तुमचे माईक बंद करा.
माने सर माईक बंद करा. माईक
बंद करा माईक. खरात सर, माने सर.
Okay, so we have got 96 participants in the meeting right now. So I think we can begin now, shall we?
Yes, sir.
Now you start now.
Okay. Thank you so much, sir. Let me introduce myself. I am Dr. Somnath Pande, IQAC Coordinator, Professor Dr. E.N.D. Patil Mahavidyalaya, Malkapur. Good afternoon, one and all. Science is poetry of reality, it is said. Therefore, it is very important that being scientists, you should have imagination. In the same vein, German theoretical physicist Albert Einstein says, the true sign of intelligence is not knowledge, but imagination. Scientists always try to make our world beautiful through their faculty of imagination. Due to their relentless efforts to discover what is unknown and hidden, today's world is what it has become now. In recent times, a new scientific field has emerged, and that is nanoscience. There has been huge amount of research going on in this area across the globe. It has been advancing the notion of thinking small. Nanotechnology, or the study and application of manipulating matter at the nanoscale, has uncovered the existence of a world that is 1,000 times smaller than a fly's eye. It has also led to the development of materials and techniques that have enhanced production capabilities. Nanotechnology continues to have a broad impact on different sectors. In fact, the worldwide market will likely exceed $125 billion by 2024, it is estimated, ranging from stain-resistant fabric to more affordable solar cells. Nanotechnology applications have been improving our daily lives. As research continues, advances in this space are opening up possibilities for more promising innovations. It is in this vein, Department of Physics and Department of Chemistry, in collaboration with Internal Quality Assurance Cell, Professor Dr. E.N.D. Patil Mahavidyalaya, Malkapur, has organized this international web seminar on novel applications of nanomaterials. For this particular webinar, we have two guest speakers. For session first, we have Dr. Bharat Kale, who is a scientist G, Director and Director General A, Center for Materials for Electronics Technology, Symmetry, Pune. And he would be talking on nanostructures and their applications. For session second, we have Dr. Girish Kaiser, School of Chemical and Process Engineering, University of Leeds, United Kingdom. His topic is effect of crystal structure on conductivity of A2B2O7 compounds. I heartily welcome all the speakers and participants. And now, may I request our Honorable Principal, Dr. Sunil Helkar, to welcome today's guest speakers and participants. Sir, over to you.
Namaskar, everybody. I am Principal Dr. Sunil Helkar. I welcome all of you, particularly speakers. Dr. Girish Kaiser, School of Chemical and Process Engineering, University of Leeds, United Kingdom. Dr. Bharat Kale, Director, Center for Materials for Electronics Technology, Symmetry, Pune. Vice Principal of our college, Mr. Shahaji Mane. IQAC Coordinator, Dr. Pande. Co-Coordinator, Mr. Kharat. Organizing Secretary, Mr. Mohan Sangle. all members of organizing committee, participants from abroad and various states and union territories of our country. Friends, our college is established in 1992 and situated at Malkapur on Kolhapur-Ratnagiri National Highway number 166 in Shahwadi Taluka, Maharashtra, India. This area is a part of Sahyadri Mountain. We call it as Western Ghats. We organized this web seminar to discuss the applications of nanomaterials. In course of time, we experienced information technology, biotechnology. Now we are in the age of nanotechnology. Nanotechnology is an umbrella term that is used to describe a variety of techniques to fabricate materials and devices on nanoscale. It is a fundamental understanding about how materials react or works at nanoscale, that is atomic, subatomic, or molecular level, in the creation and utilization of structures, devices, and systems that have novel properties and functions. Once again, I heartily welcome all of you in this online August gathering of research scholars, teachers, and scientists. Thank you very much. Over to Dr. Pandey.
Thank you so much, sir. Now, there would be online publication ceremony of our college magazine Kranti Deep in graceful presence of guest speakers of this web seminar, Dr. Bharat Kale and Dr. Girish Kaiser. For this, may I now request Mr. Pramod Kumar to share the symbolic PPT through which we are publishing our annual college magazine Kranti Deep. Kumar sir, please share the screen. We have made a small PPT and it is going to be a symbolic publication of our annual college magazine Kranti Deep. For this Kranti Deep, Chief Editor Dr. S.K. Khoth and other section editors have taken relentless efforts throughout this lockdown, despite having a lot of difficulties in conceptualizing this particular magazine. Despite all these facts, they have overcome all these difficulties, and they have beautifully created our annual magazine Kranti Deep. Kumar sir, please go ahead. This is the front page of Kranti Deep for the academic year 2019-20. The magazine consists the creative writing of our students. At the same time, various activities that have taken place during 2019-20. Okay, I declare here that Kranti Deep annual magazine of Professor Dr. E.N.D. Patil Mahavidyalaya has been published. Thank you so much. After this, we are turning towards session first. For session first, we have Dr. Bharat Kale, Scientist G, Director and Director General, Center of Materials for Electronics Technology, CIMET, Pune. May I now request Mr. Santosh Pore, Department of Chemistry, Professor Dr. E.N.D. Patil Mahavidyalaya, Malkapur, to introduce the guest speaker of the first session. Pore sir, over to you.
Thank you, Dr. Pandey. Good afternoon, everybody. I am pleased to introduce the speaker of this session, Dr. B.B. Kale sir. Dr. Bharat Kale is decorating the position of Scientist G under Government of India. He is working as Director and Director General of Center for Materials for Electronics Technology, CMET, Pune, India. Dr. Kale did his MSc in Physical Chemistry from Pune University and PhD from National Chemical Laboratory, Pune. Dr. Kale has 29 years of research experience in many fields, which includes nanostructured advanced materials, solar cells, lithium ion battery, hydrogen production from semiconductors, quantum dots in glasses, polymers, nanocomposites, supercapacitor materials, hydrogen storage materials, and fuel cell materials. Dr. Kale has a very high H index, which is 43. Sir has got 6,450 citations in international journals. Dr. Bharat Kale sir has over 260 publications in international journals of high repute like American Chemical Society and Royal Society of Chemistry. Sir has 22 patents to his credit. 22 students have obtained their PhD under his guidance, while 9 are working. Dr. Bharat Kale sir has completed 24 projects worth research grant of 190 million from national agencies. He has also completed 3 projects with financial assistance from United Kingdom, Slovenia, and Japan. He is currently working on 8 projects worth research grant of 270 million rupees. Dr. Bharat Kale sir has collaborations with scientists and research laboratories from Slovenia, United Kingdom, USA, Japan, and Royal Society of Chemistry. Dr. Bharat Kale sir has 3 technology transfers to his credit. He has delivered more than 150 invited talks. Dr. Bharat Kale sir has received many awards and honors from various national and international institutions, which include Fellow of Royal Society of Chemistry, London, APAM Academician, RSC International Collaboration with University of Leeds, United Kingdom, Senior Brainpool Fellowship Award, South Korea. Sir is editorial board member of a Springer journal. Dr. Bharat Kale sir was nominated for the prestigious Shanti Swarup Bhatnagar Award in 2010. Sir has worked as Secretary of Maharashtra Academy of Science. He is also a life member of the same. With this brief introduction, may I now request Honorable Bharat Kale sir to start his presentation. Thank you.
Thank you. Can you hear me now?
Yes, sir. You are audible.
Thanks to organizing committee, Principal Dr. Kamble, and my friend Dr. Sangle, Dr. Somnath, and other members for good efforts. I think everything is audible. That is more important today. Okay. My past experience was very bad. When we are giving the lectures, many problems we face. Hope today we'll have a good session. And thanks to Girish Kale for accepting our invitation, because in short duration we called him and he agreed to give the seminar, and you will love to hear him, because he's a very good electrochemist, and also his work is more related to industry. So I will now share my screen. So I think very recently I became the Director General, and now I have to look after all these our 3 labs. One is in Pune, where I'm the director. Another is in Thrissur. Another is in Hyderabad. Basically, Pune lab is working on nanostructured materials, polymers, organics, inorganic materials, which is required for the electronics, because electronics, nothing but all components are chemicals. Some are metals, some are ceramics, some are polymers, some are inorganic compounds, which has some electrical properties, semiconducting properties. All this is, any electronic device is a combination of all materials. So materials are very important in the electronics, because it's not a very normal materials we require. It's very high purity materials are required sometimes, 99.999. Sometimes that means 5N purity, 99.999 means 59 is a 5N purity. Like we go up to 7N purity in some of the cases. So in some of the metals, we working on Hyderabad, all kind of metals, metal semiconductors. Basically the zinc, high purity zinc, then high purity cadmium, high purity mercury, then high purity tellurium, high purity hafnium. They are required in the electronics as well as in our strategic sector, because strategic sectors is very important for us. Nobody give this because their requirement is very low. Suppose in our satellite we may require almost 200 grams, 500 grams, or maybe 5 kg, 10 kg. So industry will not provide that kind of materials to them. So Symmetry is the organization, and we government has given a thought that somebody should be there too. So under MOU we just supply them. It doesn't matter how much is the cost, but it is the indigenous supply. So that is for the strategic sectors, mean DRDO and BRNS, atomic energy, as well as ISRO, basically space satellites, and in the satellite itself, many components or many inner compounds we just introduce, and still it is a continuous process. It's the amount we require is very small, but we are doing it. Then the Hyderabad laboratories are working on metals. Then Thrissur laboratories in Kerala. It's just 20 kilometers, 100, maybe 45 to 50 kilometers from Cochin. There we working on electronic ceramics. This ceramics is nothing but the PZT materials, NTC thermistors, which is required but high temperature measurement. Then we have some substrate like aluminum oxide substrate in some of the some of the electronic devices. We have some ceramic substrates. On the ceramic substrates, they have assembled some of the components. So this electronic ceramics also very important. Like in high power electronics, we required aluminum nitride substrates, aluminum oxide substrate. The requirement is very small, and if you import a very small amount, is very huge. This one, so we are providing some of the things like aluminum nitride substrates or aluminum oxide substrates through this laboratory. Now the high power electronics is generally used in all our strategic sector, because during the functioning, that temperature goes up. In satellite, what happens? The temperature goes from minus 200 to almost 800 degrees centigrade. So such kind of things, this power electronics, the substrate and other thing was is important. So this is very important for our strategic sector. In Pune laboratory, basically, I just I would like to give more emphasis on Pune laboratory, what we are doing. Like in recently we in Hyderabad laboratory, we started making hafnium for the satellite, because in the rocket, at the nozzle of this rocket, where the fuel is going out, the temperature goes to 2500, and only hafnium works, hafnium, titanium alloy. So hafnium, titanium, and niobium together, they mix alloy, and that works. So that we have already started production, and now we are supplying almost 350 kg per year for this. So that our satellite program is very self-sufficient now. We don't have to import much from the abroad. Almost 95% to 98% we are self-sustainable in space. Because earlier we used to make, if you see 1991, we used to import almost 60% materials. Now hardly few hardwares we are importing some Russia or something like that. In Pune laboratory, we have a LTCC packaging division. LTCC packaging means any kind of electronics, we require packaging, electronic packaging. We can do electronic packaging. Suppose there are so many circuits. The circuits has to be connected each other, multi-layers. No, see, in one device it may have a number of circuits together, and they just connected each other. So this circuit has to be connected by bonding, by wire bonding, and all these things. So this kind of facility we have. We require good clean room for this, because there should not be dust between when we'd like to when we are packaging these electronics. Like suppose you have mobile has so many other inside, so many circuits, and that has to be connected. So this electronic packaging we do. Basically, this electronic packaging is very simple in mobile and other components, but in some of the devices which required in our atomic energy and DRDO, very secretive circuits, ISRO, because some of the circuits are some 25 circuits together, they want to connect it, and that should be studied. So we have created the facility, low temperature co-fired ceramic technology. Low temperature co-fired ceramic technology means at 500 degrees centigrade, we seal all these components together, and we make a sturdy device. So now we are supplying a very now the BRC gives us some kind of new designs and ask us to for many to package it, maybe 3 maybe 4 layers, 11 layers, 12 layers. Now in our facility, we can go up to 24 to 25 layers, where we can do the packaging. ISRO recently we have done it. DRDO now we are doing it. Now we are doing it for fuel cell as well. With this fuel cell, so many fuel cell has to be stacked. This stacking has been is also possible in low temperature co-fired ceramics, and we have got project from ISRO and DST, so that we can work on it. Then again, there is for the supercomputer there is a cooling system. It is also we are providing with this LTCC technique. So this very useful technique, and we are providing services to electronic industry as well as some technical services to ISRO, DRDO, and atomic energy. Then nanostructure materials, we do all kind of nanostructure materials. Like we have metal nanoparticles, metal oxide nanoparticles, then semiconductor oxides, nanoparticles. Some of them we have nanowires, nanotubes. Then we work on graphene oxide. We also work on quantum dot, carbon dots, then quantum dots of semiconductors. Then we have a technique that we can use. We can develop a nanoparticle in glass as well as polymer, and these polymers and glasses have typical applications, and that we are going to see in my lecture. So then all these nanostructures we use in solar cells, we use in fuel cells, we use in batteries, supercapacitor, because this nanostructure has wide applications. Maybe like in battery, we synthesize cathode material and anode material because these are these main components in the battery. 80% material is the only cathode and anode. So if you design a material from very low scale, maybe 5 nanometer to 10 nanometer, so we found that the capacity has been increased a lot. Further, we found that we need a very optimum size of the cathode and optimum size of the anode. Like if it is between 15 to 100 nanometer, the capacity is a normal, but it is steady. If you have a very low particle size, anyway, they are very active, so deactivation is also very fast. So initially capacity may be high, but after some few cycles, the capacity goes down and it almost become low. And actually that is not the good sign. So we optimize the parameters and found that 50 to 100 nanometers size is good for the battery applications. Then we work on hydrogen generation. This hydrogen, two sources, the hydrogen is the future fuel. People, I think you should know more about hydrogen, because now the hydrogen we are getting from the hydrocarbons, where oil refineries and where we get some little hydrogen. Then we produce hydrogen by electrolytic decomposition, where this hydrogen cost is very high. And wherever the hydrocarbons we are using, there also the hydrogen cost is very high. So how to get cheaper hydrogen? So cheaper hydrogen source is the water, and we also use H2S, hydrogen sulfide, because hydrogen sulfide, it's plenty of hydrogen sulfide we are getting from the refineries, and we are venting it out. So whether we can use it. So we design a photocatalytic process at room temperature. We get hydrogen using the photocatalyst, like semiconductor photocatalyst that we are going to see some of the slides. And we get hydrogen, and from the water, hydrogen and oxygen. And in H2S, we get hydrogen and sulfur, very colloidal, very small particles of sulfur. We get the decomposition, which can be used for the agriculture purpose. Then a good facility of thin film solar cells. And this is also silicon. Is also, we have some tin oxide based solar cells. Then dye-sensitive solar cells, we have full facility. Now we have our scientists are working on cadmium sulfide based or zinc oxide based solar cells. and fuel cells technology. We have the fuel cells. We developed a very nano catalyst like platinum, and we tried to replace platinum with some other thing like combination of other metals. And we found there is a combination where we get the equivalent amount of efficiency of the fuel cells of the catalyst. And we have also demonstrated the fuel cell of PM fuel cell of 180 watt. Now SOFC fuel cells we are trying with LTCC packaging. There the LTCC packaging is a very sturdy packaging, then very lightweight and we can stack many solar cells, many cells. So that is the advantage in the LTCC in one pack. Then we have full-fledged high energy storage material devices. Since we work on hydrogen, so we have hydrogen storage wing. People are working on hydrogen storage materials like silica SPS. Then some of the recently our people have also introduced very porous carbon from biomass. So this kind of for the hydrogen storage, this kind of materials they have prepared for the hydrogen storage. The hydrogen storage today's problem is that unless and until we have by volume around 6 liter, 6% volume or 6 to 7%, then it is feasible, because if you have very low, then we can the amount of material goes up, and that will not be feasible. So people are trying so whether we can get from 9% to 10% or 11%, something like that. Then it's very easy to store hydrogen, and we can use this hydrogen storage material for automobile applications. Suppose you want to run the bike. In bike we can just pressurize the hydrogen in that solid, and that solid can be used slow release of hydrogen for as a fuel. So that is the now you might have seen recently I have visited to BHU that we were having one project together. There we have made one 3-wheeler using this hydrogen fuel cell, and there we use this hydrogen storage material because I think with the weight of the material was 3 kg, 3.5 kg. It is a combination of carbon and something else. So this is required for if you want to use this hydrogen, put it into automobile application. So how much hydrogen we can store in the materials is very important. Then lithium ion battery. See, anything energy has to be stored and use it whenever required. We need a battery. So current batteries technology is a lead acid battery. Efficiency is low, heavy weight. All these things are, everybody knows that, and that's why lithium ion battery has come in picture, because it's a lightweight and use higher capacity. The lead acid battery, the capacity is 30 milliampere hour per gram. Then this same Li battery can go up to 120, 130. In low, some of the materials it can go up to 175 milliampere hours per gram. So it's huge capacity difference between. So the weight of the battery goes down because of this higher capacity, and it's a lightweight. Problem of lithium is availability of lithium. So we started working on sodium, and now we are very close to some of the. We have made some cells, and we are very close to lithium ion battery capacity using this sodium ion. Then flexible batteries. See, in future, all your electronic devices will be flexible or bendable, you can say. Now, If you see all Samsung TVs have got bendable Samsung TVs or foldable Samsung TVs. Then mobiles also, rollable mobiles will come very soon, maybe 2-3 years. So this kind of flexible electronics required a flexible batteries. So we made flexible batteries, and we are very close to some of the prototypes. We can roll it. Our batteries can be rolled like on pen or anything. Or now we have made a watches. Inside the watches, the battery is fixed in the belt, bendable belt. So that is which we have made now. Then metal air batteries. This lithium ion battery capacity up to 140, 130 now, in some of the 175. But metal air batteries can go up to 300 to 350 lithium air at least. So the capacity is maybe high, but it has some problems like cycles. So we initially may get good cycle, the capacity, but during cycling, this oxidation takes place and we get a very drastic capacity fading. So this is a problem with this metal air batteries. Then sensors, we work on all kind of gas sensors: hydrogen, oxygen, methane, NOx, with this metal oxide base as well as LTCC based pressure sensors. LTCC based pressure sensors is a magnetic sensors we work on. And this is basically we work for the ISRO and DRDO. They need this pressure sensors and magnetic sensors and temperature sensors. Lower temperature from 0 to 100 and 0 to 500. Then we have 500 to 1000. Then recently we started our working on NPK sensor. Most of the NPK sensors we would like to develop in optical sensors, because NPK sensors are available in the market and it takes long time to analysis. So this soil analysis, then some biomass analysis, we can use this NPK sensors, optical sensors, so farmers can use on the spot. So this is the advantage of this optical sensors. Then materials for strategic sectors, there's thermoelectric materials like in our nuclear reactor systems, the outer temperature may be some 800 to 900 degrees centigrade. Using this heat, whether we can generate the electricity. This thermoelectric material will take, it will be the good material. We have its Peltier effect and Seebeck effect. Through the Seebeck effect, we can generate the electricity, and Peltier effect, when we apply little voltage to these materials, at the end, we get the cooling properties. Whether we can use this property, whether we can use this Peltier effect and make some small type of prototype of coolers for the farmers, because this kind of device doesn't require much maintenance. Initial cost may be high, but the operating cost is very less. So that we are thinking that with a small coolers can be made for the farmers, where they can they will use it for preserving crops like grains, then fruits. Milk is a big problem, because you might have seen in Mumbai, almost when milk come to Mumbai, to almost 20% milk get wasted because of this problem, cooling effect. They are not getting good cooling during the transport. So this kind of thermoelectric materials can be used, such kind of preserving milk, where at least 10 degree, maintaining 10 degrees is not a big problem using these thermoelectric. So this is these are the materials presently we are working. Now we started working on some of the good additive manufacturing area, where additive manufacturing is the area we can now. Why this additive manufacturing is required? Because the advantage of additive manufacturing is, suppose any automobile part we want to make it. So if you have a design of automobile that part, and you have all these kind of machines, you can make it at home. Suppose it's a servicing center, and that servicing center that want that typical part, they can have this machine and use it and make that part. The cost of part, see, suppose it's very general rule that suppose you make it in huge quantities, cost will come down. Additive manufacturing, whether you make one or you can make 10, cost will be same. So that is the advantage of this additive manufacturing. So through this additive manufacturing, we would like to make batteries, because cathode, anode, by just printing it, and if we have solid state electrolyte, that also we can print it and make batteries through this additive manufacturing. Then solar cells, there's all kind of electronic devices can be made. Then aeronautical part also can be with this additive manufacturing. So this work we have already initiated. So we have a state of art of all these facilities, because it's required whenever we are talking about any materials, then we need to have such kind of facilities. Basic facilities are X-ray machines, then XRD, then scanning electron microscope, then you have scanning electron, then you have 3D emission transmission electron microscope. There we have AFM, SPM. Then recently we added 3D X-rays, because whenever we are making some kind of circuits and devices, suppose there are pinholes in the circuits, we can find out through the 3D X-rays. Then electrochemical workstation, we have impedance, thickness measurement, all this we have, and because these are required for the battery. This is our battery fabrication facility. You can see there are almost 19 equipments. If you suppose you want to make a battery here in the glow box inside the, so from cathode, anode preparation, electrode preparation, then drying, then sealing. This is a sealing facility here. Okay. Then again, electrolyte filling facilities, because today we do not have technology for the solid state battery. So all electrolytes today we are using it is the organic electrolyte. This organic electrolyte is hydroscopic. So whenever you want to seal the battery along with the electrolyte, then it has to be transported into a glow box, and then there we have to fill this cell. Then we can make single cells out of it, and then make a required batteries. So this is state-of-art facilities we established in our laboratory. Almost 19 students are working on this now, this lithium ion battery area. Now we have made a center of excellence in rechargeable batteries in cement with some additional facility. So any startups or anybody can work, anybody wants to work in the area of battery and do the prototyping and all these things. Now it is possible through this center. So this center is almost 20.85 crores we have put in, and there are many other industries also working. They poured the money. It is not that only government has poured in. There are two companies. They have almost invested 8 crores in this project. So now this will be self-sustainable model after 5-6 years. These centers will have some profit. So now this, using our facility, we have made cathode, lithium cobalt oxide, then we combination of this replacement of cobalt with some nickel, some manganese, that also we are doing. Then lithium iron phosphate, these are the 3 cathode materials we have now optimized, and up to 100 grams, 500 gram scale now we are coming up. Then anode materials basically are the lithium titanium oxide, and this also we have established. And the hard carbon is another. Suppose you want to have the batteries of beyond cells beyond 3.5 volt, 3 volt, then we have to use carbon. And for the 1.5 volt to 1.5 to 2 volt, we can use this lithium titanium oxide as an anode. The advantage of lithium titanium oxide is it's very stable, and it doesn't react with easily with the electrolyte. Carbon sometimes get deactivated due to the electrolyte, and hence in hard carbon the major problem is the capacity fading. Initially we have to 300 milliamperes, but after few cycles then we may have some 100, 120. So again, this is a big problem with the carbonious material. Then we started working on biomass like potato and banana and made a carbon out of it, and some kind of other biomass. So we made a porous carbon, we made a mesoporous carbon, we made a graphene out of it, graphene-like structure. And it's a graphene-like structure, and graphene has a holes, porous graphene, you can see. Some 20 nanometer, 30 nanometer holes to this. Deliberately we did that for the good porosity. So we can have button cells fabrication here in Pune, and we can also have hard carbon. We can also have pouch cells. You can see the pouch cells here. These are the pouch cells, these are the button cells, and these are the pouch cells. Capacity we established 120 milliampere, 120 milliamperes. It's very consistent up to 1000 cycles. And we use carbon as well as we use is a graphite, you can see 3.7 volt, and lithium titanium oxide we generally 2.6 volt maximum, but stable is a 2. Then efficiency we are almost more than 80% we observe. Working temperature -10 to 60. Now we are trying still lower temperature. Geometry, we have button cells, rectangular flat cells. So we can make 2032. Now we have good facility for making pouch cells. So stacking of pouch cells, then we can make batteries for mobiles. So each mobile, we have 24 stacking of single cells. Means 24 cells we have to together and make it, connect it parallelly and in series for voltage and parallelly for the capacity. So we have good, if you have good BMS out of it, then we can design and we can stack these cells, and we can make this single cells means it's the 120 milliampere hours per gram. Suppose you want to make 2000 milliampere battery or 5000 milliampere battery, then this single cell has to be stacked up the required number. You can see here, suppose this is a cylindrical cell. In the cylindrical cell, we have so many single cells. You see here, carbon, cathode, anode separator, cathode, anode separator. So one cell is a cathode, anode separator, something. So such, see, 18650 has a capacity around 2000 milliampere hours per gram. So the stacking of almost 20 to 24 single cells, and then we get 2000 milliampere or 5000 milliamperes. So, so the battery means the combination of single cells. We have required capacity. Like suppose required voltage unit 72 volt. or 24 volt. Accordingly, your BMS changes, and you have to design the batteries. So we made the battery for the mobile, very rough, because we did not have the packaging. So we made a pouch cell of 24 stacking, and it charged around 1 hour for these mobiles and all this that we have demonstrated. Then now we are getting a cylindrical cell facility. Now in the market, which we are getting lithium ion battery is a cylindrical. That code number is 18650. Code number means 18 mm is a diameter, and 60 mm is a height, something like that. And another is 21700. So both the facilities now will have. Now, within this year, we are going to make some 1,000 cells of 18650. 1,000 cells. Because these 1,000 cells we required in, now we would like to link with supercapacitor, that I will come later. So this facility, I wanted to show you that this facility is now available with us, and we can make cylindrical cells for any devices and all this. This is our roadmap. So we are going towards e-vehicle. Okay, so we are now here, design development of anode cathode. Now this packaging of modules and manufacture, this we are going to take with center of excellence. So we have this center of excellence will do this job, and see, as government has already declared that we should have our own battery manufacturing. So initially, it is not possible. Initially, somebody will import this technology. But somebody should be there to support this technology initially, because a lot of work is involved in this. Because nowadays you are importing all kind of machineries from the China. Since earlier there was no demand, now demand is coming. Now it is our duty to design equipment also. So in this center of excellence, we involve some of the industries. They can design the equipments, like now coating machine, slitting machine, sealing machine. Okay, all this comes from China. So we would like to develop in this center of excellence, and immediately industry will be there. Technology transfer, they will. We can do them, and we can further take up in the industry. So battery industry will be self-sustainable after 4 or 5 years. Any equipment they require, if somebody should be in India, they should be able to give. So we have to make such kind of arrangement in future. Now the instructions are there. We will make everything in India. So there's a lot of demand will be there. A lot of expertise are required. Many industries should come forward. All these startups will have opportunities because government is promoting that. And then flexible batteries is the future. We have to be ready with future technology, so that we are doing it. So this kind of all structures, like we made MOS2 as anode, cadmium indium sulfide is anode, lithium manganese oxide, zinc indium sulfide, RGO, reduced graphene oxide with this combination also we tried. And we published many papers on this, and this RGO, zinc indium sulfide, and MOS2 graphene, this kind of materials gave good capacity and almost 1,000 cycles and all these things. So that also I would like to share in my, I don't know, I have slide or not, but now we have stabilized some of the materials which can give good capacity. Because cathode has a less capacity, cannot go beyond 200, I can say, for like NMC. If you want to compensate that, then we should have the anode, very stable anode, which can enhance capacity up to 300. So whether it is possible or not, I don't know. But through the theoretical calculation, it shows we can go up to 300. So this is the MOS2 honeycomb-like structure. So this lithium ion shows something like that 400 milliamperes hours per gram is a good capacity as using as an anode. Now we are making the full cells. We have not made full cells. We have made half cells. We made the standardization with lithium foil. Now, instead of lithium foil, we can use any lithium cathode like lithium cobalt oxide and this MOS2 together and see the performance. So it comes down to 200 also is fine. So, and this kind of structure is required because when charging, temperature goes to, during charging, lithium ion goes to anode and discharging from anode to cathode. So this kind of transport and intercalation in the anode is very important. So almost all lithium sits on the layer of the anode while charging, and discharging. While discharging, it goes back to cathode. So that is the cycle, one cycle. So this kind of structure is very important. So instead of MOS2, then we thought that whether we can have copper sulfide with MOS2, but we find that while if you do the copper sulfide as a together with MOS2 as a heterostructure, this copper sulfide has a less. It's not very stable like MOS2, and it gets decomposed. This structure is very important. Structure like layer structure we can see here. So but the capacity we found is very less, and capacity fading we observe. Another new class we developed like NaFeMO4 and LaFeMO4. These two like MO4 series we invented. Means we would like to have the we would like to study the crystal structure of this both the compounds because it's not available. And we'd like to little modify because very stable capacity we get 100 milliampere hour per up to 500 cycles. For sodium ion, you can see for sodium we get this much 100. But if you modify this, then definitely it can be increased. And so we'd like to, our students working on this, many students working on this MO4 based. One group is working on PO4 based material and one on the MO4 based materials, and another is conventional. So both the things we have to keep in mind and work for better batteries. And this is actually the so we have full-fledged sodium ion battery group, and they are working on tin-based anode as well as silicon-based anode, silicon tin-based anode. And we started doping with carbon. We started doping with phosphorus because stability of SNO2 is very, very low. Though the theoretical capacity of SNO2 is good, very high, but the problem of capacity fading we need to sort out. So we are working on that. As I mentioned, these are the graphenes, very perforated graphene. You see, I made a circles. It may be around 20 nanometers pores, which is graphene. So deliberately we made, and this is made out of the flower biomass, where we can see it's a graphene-like structure. Distorted, we say that a distorted graphene-like structure, and it has some pores. And this graphene gave good lithium ion capacity, almost 200, and sodium ion capacity we got here 125. So we are more concentrating on this, whether we can go further for sodium ion battery in this using this material. Then flexible cells, we are making it. You can see that flexible cells, we have made a rollable cell. So we can roll it still, we can see that the intensity is not coming down. And that is the materials we made out of our polymer electrolyte. You can see our polymer electrolyte here. And this polymer electrolyte we developed. But still we have a problem in this polymer electrolyte. It can go up to 200 cycles, more than 200 cycles. Still we are facing problem. So we are modifying this electrolyte. See, here is, you can see more precisely. And I don't know if video is working. It's not working. No, it will not. So you can see here, you can roll it, these batteries. Okay. And here in these batteries, we have a lithium phosphate, LiPo4, then lithium foil. So one side is a lithium foil, another side is our material. And in between, we have polymer electrolyte. Then we did a bendable study. Very good. We can 0 degree, then 45 degree, 90 degree, 180 degree. And there is no much, you can see, though C rate is very high, and there is no much change. So still we are working on it. So out of this, we made a belt, very long belt of this flexible battery cell, which has 80 milliampere hours per gram. Now we are working with all these industries now, KPIT, Software Technologies for the medium, this one, sodium, then Bharat Electronics for reserve batteries, and sodium ion to industry, then DST, cylindrical cell fabrication with a niche joint project with Johrat in Assam and other projects. Then we worked on flexible solid state supercapacitor. So here we are working with VNIT Nagpur. VNIT Nagpur is taking care of making flexible cells. Now we are giving them these powders out of gel. Very 900 meters per gram of BET. Now we are developing some solid state and flexible supercapacitor. Then we have prototype development fuel cell using nano-functional materials like you see, platinum is the best material for as a catalyst for this nano catalyst for this fuel cell. But we replace with cobalt and carbon, and we get the same capacity. So now we have demonstrated 80 ampere and 180 watt fuel cell. This you can see in the corner, this stack of fuel cell. It's around 80 ampere and 180 watt capacity. Then we had a sensors as Girish. Girish is expert in the sensor. Girish is a very long, many papers in the sensors, I know. And we started working on these sensors, like metal oxide sensors, NOx sensor we have made for the ISRO. And we have demonstrated this device for these NOx sensors. And now we are making hydrogen and ammonia. This is a temperature sensor. This is based on the ferrite-based material, manganese-based ferrite. And this, we developed the composition at 500 degree Celsius and 1000 degrees Celsius. So one sensor can go up to 500 degrees centigrade of sensitivity, 0.1 degree, and 1000 also 0.1 degree, something like that. This is basically DRDO, for DRDO we developed because they are the turbines. One part is they are going to very low temperature, and another turbine they got to very high temperature up to 1000 degrees centigrade. So both the sensors we developed for this DRDO. Then development of microcrystalline silver powder. See, this silver powder is nanopowder is required in photovoltaic cells or as a conducting test and EMI shielding applications. So we have Madison Metal Limited in Mumbai. They are in the silver business. they make silver ornaments, gold ornaments, and they have a lot of silver, waste silver, because during cutting something, they have waste silver, some waste solution of silver also. So we use that solution, and we developed 100 gram batch scale nano silver powder technology for them. Now they are then we have given the silver. We have also developed the silver paste composition, silver ink composition, and give it to them. So this is the industry project. Within it was only 1 year project, and we finished within 6-7 months, and now trials are going on there. Then Manganese Ore India Limited, they have gold mines. 75 mines are owned by Moil India Limited in Nagpur, around Madhya Pradesh. So they have a lot of manganese sulfate waste, because during leaching this manganese sulfate comes out, and we use this manganese sulfate and give them technology of ferrite manufacturing technology. Like we did the ferrites for them, composition using manganese and iron oxide, also their iron oxide coming from their waste. And now this project is already completed. Now we are getting 3 more projects from the Moil for this, making some value-added compounds for them. Then thermoelectric material. Thermoelectric material, I to explain you. One is a Peltier effect and another is a Seebeck effect. So this Peltier effect, this palladium telluride is a good material. We can get ZT around 1.2, something like that, and we can use it for the cooling devices. So we just make a powder now, palladium telluride, lead telluride. This lead telluride and palladium telluride, not much difference, but lead is banned, so we are talking about palladium, so it's costly. So we made around 20 to 30 nanometer powders, and now we are making PN junctions and making devices. Then is hydrogen. Hydrogen is a future fuel, I told you. So how this hydrogen is used for the fuel cell, as well as direct hydrogen engine also come in the market, and we can use direct hydrogen. It's a very green fuel. So, and now latest news is that now people are more talking about hydrogen, because everybody feels that hydrogen is the next energy technology is the hydrogen. So it will have future again. So we have started working on it. Our process is at room temperature. We are making hydrogen with photocatalyst. So we are developing photocatalyst at room temperature. Sunlight falls on the photocatalyst. Electrons and holes are generated, and these electrons and holes are responsible for reduction and oxidation. Okay. So this is very simple photocatalytic process. So there is a trick in this, that how we can trap electrons and holes. If you want to reduce water into hydrogen and oxygen, so you want to, so first thing is that maximum electron and holes have to be generated. So your photocatalyst should absorb more sunlight, more natural sunlight, and will produce more hydrogen, more electrons and holes pairs. And then second part is how you can trap the holes and make a free electrons. And these free electrons are responsible for the hydrogen production. Then H2S you have. So this is the conventional method for hydrogen. So steam reforming is the main process. Okay. And the steam reforming, we get carbon monoxide and hydrogen. Carbon monoxide, hydrogen mixture, and this separation is a problem. All these kind of things, very complicated. So hydrogen cost goes up. So the simple hydrogen method is a photocatalytic process which you are processing. Then H2S. Now in refineries, H2S get oxidized to H2 and sulfur. Okay. So, and this process is already there in the market, but it's very corrosive process, and temperature is 800, 900 degrees centigrade, and H2S get converted to water and sulfur. It's a liquid sulfur used for the agriculture purpose. From our process, we can have H2 and colloidal sulfur. That is the advantage. So these are the all catalysts we developed. Very nanostructured catalyst. You can see all are nanostructures. These are the flower-like structure. Very thin petals get assembled and form flower-like structure. Same material in the form of carbon, in the form of nanotubes. See, 17 nanometer diameter of carbon nanotubes. You can see here. Okay. So, and here, and then lanthanum indium sulfide series, zinc indium sulfide series. Zinc indium sulfide series, you have a hollow structure. You have hollow nanostructures. Then we have a rose-like structure, very thin petals in the flowers. These are important because the surface area is increased drastically using this such kind of structure. And so the morphology of nanostructure is also important for any kind of application that I would like to convey this. And this is the reactor we installed at the roof of the laboratory, where all sunlight is available from 11 to 4 o'clock. So we started working on this for huge large scale. Maybe we established 2 liters per hour capacity. This is the glass. In the glass, we develop silver phosphate nanocrystals. Silver phosphate is a very unstable compound. When silver phosphate, you keep it in open, immediately silver gets oxidized. Okay. And if you stabilize in glass, see the glass we have stabilized, and inside the glass we can see the particles here. It is transmission electron microscope I have shown you. Okay, it's very important, and they are uniform color shows that there is uniform distribution of nanoparticles. If you break the glass, anywhere you analyze the same structure, same density you can see in this glass. So this glass we would like to use as optical cutoff filter in photonic applications, because it will have good applications. If you control the size, up to 1 nanometer, 2 nanometer, definitely it will have so many other applications. Then very typical example I will show you hydrogen is when you have bismuth nanoparticle in glass. And why we use this bismuth nanoparticle in glass? Because it covers whole spectrum of solar light, absorb the sunlight. Okay, and because of that, you get a huge amount of hydrogen. We use this glass as a catalyst for the first time. We have US patent on this. So you see 11,541 the micromole per hour. It's almost 500 ml per hour, something like that. And see, particle size inside the glass is 2 to 3 nanometers, in some of the 8 nanometers, okay, in the glass, and they are uniformly distributed. So first time we have shown that the glass can also work as a photocatalyst, and it will be stable. The beauty of this photocatalyst is that it doesn't deactivate easily, because it's steady. And as soon, suppose you do number of experiments and take it out the glass, wash it with the water, normal water, use it again, you will get the same capacity. That is the advantage. This is the reactor we use. I showed you. Now we are working on this. Then same quantum dot glass we use for water purification. This work is going on with the Royal Society of Chemistry along with the University of Leeds. Now still some work is going on in this, because this quantum dot of The bismuth telluride, bismuth sulfide we have inside the glass. If sunlight falls on it, these glasses, because absorb the IR rays, so heat is generated and this boil is get heated up to 90 degrees centigrade, and then we purify the water. So this is the concept. So now we have made a setup in IIT BHU of this kind of thing, where we can take the larger trials of this glass. Then this is nano coating developed by Cement. See, generally this apron contain a lead, because lead is good X-ray absorber. This is whenever orthopedic doctor, you go to orthopedic doctor, and this kind of aprons they wear, because if they want to work under X-rays system, then this X-ray absorbers they use it. The weight of this apron is 8 kg. Our nano coating is 3 kg. That is the difference. So doctors are very happy with this kind of analysis. Then we made a optical sensors, photonic sensors for light sensors. So this is cadmium sulfide based light sensors. This is used in automobile. When some car is coming from the front side, so the deeper can off when it comes closer to that. When both cars are coming closer, then their deeper gets off when you get this kind of sensors. Generally, what happens now, we see all cars are going, and when they are coming near to also, they don't do that, because the focus is on our eyes and we get disturbed. But if this kind of sensors are there, they automatically get deeper, will be from 100, some 100, 100 and 200 meter distance, it get, this may be censored. So these technologies we have already transferred. So these all kind of sensors will come in the market within 1 or 2 months. Then this is our thin-film solar cells we are making. Very good, very steady cells we make, but still we are working with efficiency. This is a full facility of fabrication that I'm not going into details. Then we can make nanoparticles on large scale here. This is a plasma reactor. In this plasma reactor, one of the cathode is metal. Suppose I want to make aluminum nanoparticle, the aluminum can be put as one cathode and make as a, this temperature goes to 8,000 degrees centigrade, 3,000 to 4,000 degrees. Aluminum get evaporated, and this at atomic level it gets quenched, and that we get nanopowders of 20 nanometer, 30 nanometer, 100 nanometer. The advantage of this, the scaling up of the nanoparticles is very easy in this. We get 100 grams per hour capacity of the nanoparticles, any kind of metal nanoparticle, metal oxide, metal nitrate. So this is very unique machines we have. We develop with Techna, Canada. This is aluminum nanopowder we developed in this. You can see very sharp peak. This is a very sharp peak because these aluminum particles are highly crystalline. Though it is smaller particles, they get agglomerated. When you disperse it, again they will get separated. So here you can see. These you can see the bigger balls. With bigger balls in the thing where the many particles come together and forms this kind of balls, which we can observe in the transmission electron. The copper nanoparticles are the same. 20 to 25 nanometer, 50 nanometer nanoparticles we can make. And this is the, you can say 100 nanometer, 100 grams per hour capacity we can have using this machine. And then we make quantum dots in glasses, means all kind of cadmium sulfide, cadmium selenide, bismuth selenide, bismuth telluride, all kind of material, all kind of material of quantum dots we can grow in the glass. So that means you can have the glass of band gap from 3.4 electron volt to almost 1.2 electron volt. You can see here. all these glasses have different quantum dots inside the glasses. So it gives different colors. Here you can see the different colors. See, it is a cadmium sulfide glass. Okay, it may be 2.5 nanometer, 3 nanometer, 4 nanometer, 5 nanometer. So with quantum dots, it changes the color. Accordingly, absorption also changes. So see, size sensitive is quantum dots. See the size sensitivity with the optical spectra, which clearly shows the how this shift with the size. This is bismuth sulfide quantum dots glasses, and we observed that this glass can be used as an X-ray absorber. Instead of lead, we can use these very small nanoparticles of this small nanoparticles of this compound inside the glass, which can absorb it. It's a transparent glass. It's a transparent glass. Inside the transparent glass, this is the nanoparticles we can see. So this is my then we also started working on neutrino energy, where this neutrino photovoltaic whether we can see is around in atmosphere. A lot of energy is available. Whether we can catch up this energy and make devices out of it with some materials, which this kind of like 2D materials now people are talking about, like graphene-like structure with quantum dots of silicon and quantum dots of boron and all these things. It will work, people say. And now we are doing some theoretical study out of it and see how we can use of this. So thank you very much. I feel I have taken almost, I've finished in time. And there are a lot many things we can do. This is only 25% of our work I have presented, and because then otherwise it is very difficult to cover all. So within the short time, I can I could do only the I could cover all almost all, very not in depth but superficially. But you can ask the questions, whatever maybe I have presented, and anything on this. Any questions on this? No problem. Thank you very much, and thanks a lot. Any questions? If you can ask, you can ask.
Thank you so much, sir. Participants are requested. The stage is open to ask questions. So you can ask your questions through chat box.
Okay.
I request Kaiser, please stop sharing your screen so that we could.
Okay, I'll do that.
All right, thank you so much, sir. Now participants are requested to ask their questions through chat box. We have to wait for that. I think participants are writing their questions.
Sir, one question asked from H.V. Desai College, Dr. Gogle. He asked how we can use this sensor in developing different equipments or apparatus. Those can be used in this COVID-19 scenario at low or reasonable cost for common man.
So now these sensors, we can, he's talking about biosensors. If you want to make for COVID, okay, for this COVID-19, then you can make a biosensor which we can measure the antibodies. How many antibodies can be increased or get reduced? So that kind of sensor we can make through the plasma technologies. means that silver plasmonic effect. If you have silver nanomaterials or cobalt, gold nanomaterials, it gives the plasmonic effect. Through this plasmonic effect, suppose antibody sits on this plasmon, then this plasmon gets shifted. So through this we can make this this kind of sensor. But all our gas sensors cannot be used here. Only biosensor can be used. So we are working on the plasmonic sensors, which can measure the antibodies. Okay. So that is only the thing we can do with this COVID.
Sir, there is one more question from Pramod Desai. Is there any work being carried on C-dots for drug delivery and vaccine-related aspects in Symmetry, Pune?
Because that is not our area, so we are not working on that. We just what you did that quantum dot of carbon and quantum dot of zinc oxide and silver. We made a mask out of it because these quantum dots are giving good antiviral study. Because in 2013 or 14 we made a study and we found that the ROS of cells get increased with this material. And this will be useful for damaging the walls of the viruses. And we made almost 1,200 masks supplied to all hospitals, police departments. They are using it. Now we are working on how to make a curtains out of it, so that all hospitals, bed sheets of hospitals can be made out of this coatings. It's a very thin coating. Each mask have only 20 milligrams of coating. It costs around 30 rupees, 30 paisa. So it is very cheaper. That we have already developed. Now we are announced this technology will come in the market because this is under clinical trial. 2 trials already done. One trial is, if that one trial is finished, then we can have this antiviral mask in the market. When the viruses sit on the antiviral this mask, there it has the viruses has the coating of fatty acids. And this fatty acid has that sulfur group, and that sulfur group is get attached with this nanoparticle and that get damaged. So deactivation of virus is possible because of this nanoparticles. And that study we have done with D.Y. Patil Medical College now. We are working on Dr. Raut is there in the nanoparticle. They are studying it. Antibacterial, no problem. All bacteria kills. That already we have done. We have shown that during this, when we have a small piece of this mask and put it in that, we studied with all kind of cells, bacteria, and we found that small piece get killed all kind of bacteria. So that already we have done it. Only this antiviral study, 2-3 stages we have to do because it's long process. That we under process, we may be within 2 or 3 days we may get certificate, and then we can go in the market. Otherwise, difficult. Though, but we are supplied to all hospitals, and our own people have started using it. Our mask now, so they are very quite safe. And you might have seen that Symmetry is the first organization has developed the swabs for the testing, because the polymer swabs was totally imported from the China and other countries. The initial cost was 450 rupees. Now we are getting at 5 rupees cost. So before March, the cost of swab was 450 rupees per swab. Swab means when they take the sample, doing that sample, you have a stick and that they are putting the mouth that sticks. Okay. Is developed, and that now the market has gone down. Now initially was 450 rupees, now 7 rupees. Okay, so kit, the earlier kit was almost 9,000 to 10,000 per kit. Now it has come down to 1,200 of this. So that will help for the country, where we drastically reduce the cost of swabs. These are the two things we did for COVID-19 now. Okay. Anything else? Any questions? Is it possible to generate hydrogen as a fuel from water using specific nanomaterial at the modest cost? Yes, it is a modest cost, is like TiO2 with doped with nitrogen. It's a very low cost. We can generate hydrogen at very low cost. Then another question. I don't find any other questions.
I think due to time constraints, sir, we have to.
Okay.
We have to finish our question and answer session for this first session.
Mm-hmm.
Thank you so much, sir, for your wonderful presentation. I'm sure that our participants must have enjoyed your session, and I thank you so much for this. I must say that Symmetry has been headed by a very smart brain with strong shoulders. So I thank you so much, sir.
Thank you very much.
For the second, now we are turning towards the second session. For second session, we have Dr. Girish Kaiser, School of Chemical and Process Engineering, University of Leeds, United Kingdom. His topic is effect of crystal structure on conductivity of A2B2O7 compounds. Now, for this, may I now request Mr. Pramod Kumbhar, Department of Chemistry, Professor Dr. N.D. Patil Mahavidyalaya, to introduce the guest speaker of the second session. Kumbhar sir, over to you.
Thank you, Pandey sir. Good afternoon to everyone. On the occasion of International Web Seminar on Novel Applications of Nanomaterials, Professor Dr. N.D. Patil Mahavidyalaya, Malkapur. I take the privilege to introduce the resource person of second session, Dr. Girish Kaiser. He is working in the position of reader at School of Chemical and Process Engineering of University of Leeds, United Kingdom. He has completed his PhD from a reputed Indian institute, that is Indian Institute of Science, Bangalore. His areas of expertise are solid-state electrochemistry, ionic conductors, sensor technology, refractories, nanomaterials, impedance spectroscopy, high temperature materials chemistry, phase equilibrium, and thermodynamics. His research career has been dedicated to research into advanced functional materials for electrochemical sensor technology, ranging from ambient temperature to high temperature aggressive environments such as combustion and metallurgical processes. The research involves both experimental and theoretical analysis. His research has been supported by government funding bodies and national and international industries. Main funding bodies include Engineering and Physical Science Research Council, EPSRC, Innovate UK, Department of Trade and Industry, Royal Society, Royal Academy of Engineering, and European Commission. He has organized several research symposia. His research output has been published in a range of international journals related to analytical chemistry, solid-state ionics, materials chemistry, materials science, and engineering. Dr. Kaiser has authored more than 135 research articles in internationally peer-reviewed journals and more than 85 conference presentations, of which several have been as an invited or keynote speaker in international conferences in USA, Canada, Europe, Singapore, India, and China. He is a fellow of Institute of Materials, Metals and Minerals UK, member of Board of Review of Materials and Metallurgical Transactions B, published by TMS USA, member of Executive Committee of Sensors Division of the Electrochemical Society USA, member of Executive Committee of Materials Chemistry IOM3, etc. He has collaborations with research groups and institutes such as Applied Photon Science, Complex Systems and Processes, and Functional Materials. So, with this brief introduction, I welcome Dr. Girish Kaiser and all participants. No doubt, the person of great research caliber is among us today. I request him to entitled Effect of Crystal Structure on Conductivity of A2B2O7 Compounds. Thank you. Thank you, sir.
So thank you very much, Professor Kumar, for your kind introduction. And it's a great pleasure to give this seminar or webinar as it stands today in front of distinguished audience. It's a great pleasure to be along with you all today and share some of my thoughts on a focused area of research that I am going to present today. Today I will be talking about effect of crystal structure on conductivity of A2B2O7, which actually crystallizes in both pyrochlore as well as fluoride structure. So it undergoes order-disorder transformation. And I think there are special properties in this particular material because of its flexibility in structure and flexibility of accommodating wide range of cations from the periodic table, so trivalent and tetravalent cations from the periodic table. So before I go into my actual presentation, I would like to show you a bit of what is Leeds University and where it is on the map of UK, particularly for those who have not visited Leeds or know about University of Leeds. University of Leeds is a very large university. It is the largest single campus university in Europe. So all the departments of Leeds University are positioned on a single campus. We have about 52 different departments, research departments across the campus. And they are all divided into or segregated into 9 different schools across the 9 different faculties across the campus. So we have 52 schools segregated into 9 different faculties. We have all the engineering and science departments in a super faculty, which comprises of I think 9 different schools, and it is called Faculty of Engineering and Physical Sciences. So this has been a recent reorganization, which happened actually in last year of August. So we merged the engineering faculty with science faculty to align ourselves with the funding council, which is Engineering and Physical Science Research Council of UK. So we have created a super faculty, which is also called as Engineering and Physical Sciences faculty in the University of Leeds. University of Leeds has about 35,000 students, undergraduate students, which actually includes about 15,000 postgraduate students and about 4,000 to 5,000 postdoctoral research fellows across the campus. The number of faculties, I think, are about 15,000. Sorry, the member of staff are about 15,000. And out of that, there are about 5,000 faculty members in different schools. School of Chemical Process, and Process Engineering is the largest school on the campus with about 45 members of staff. So we have research areas which include chemical engineering, hardcore chemical engineering, and materials engineering, and also research areas that are at the interface of chemical engineering and material science and engineering. So I belong to the material science and engineering group. So this is the main building. I don't know whether you can see my cursor there. So this is the main entrance, which is called as the Parkinson's building of the university. So university started in 1902 or 1903, around that time. In fact, the first, so university got the charter in 1902 or 1903, around that time. However, University of Leeds, the first graduate that came out of University of Leeds was in 1874. So you can see that it is a very old university and is one of the red brick universities. It's called one of the red brick university in the UK. So University of Leeds.
Sir, excuse me, sir.
Yeah.
Maybe your screen.
Sorry?
You started your presentation, however. Sorry to interrupt you, but your screen is not being shared right now. So please share your screen and.
I thought I had shared my screen. Okay, let me see if I can. So are you able to see now?
No.
I did share the screen. Are you able to see the screen now?
Yes, sir. Please go ahead. Now you have started sharing your screen.
Okay. Sorry about that. So yeah, I think as I was saying, so this is the University of Leeds main entrance. So that's the University of Leeds main entrance. And if you look at this, this is the enlarged view of University of Leeds. And if you go to the far end of this particular building, then that is where we have a School of Chemical and Process Engineering, which is organized into 6 different floors on the at the north end of the campus. Leeds is roughly halfway between so it sits on the spine of United Kingdom. So that is where Leeds is. So it sits on the spine of the United Kingdom. The United Kingdom is made up of England, Wales, and Scotland and Northern Ireland. So if you look at this, that is where Leeds is, and University of Leeds is at the moment rated at as the top 100 universities in the UK. So it's a very research-based university. So our main mission is to train and educate excellent future generation for the benefit of United Kingdom as well as for the rest of the world. So with this little introduction of University of Leeds and School of Chemical and Process Engineering, and also the faculties that are within the University of Leeds, I will try to move on to my next slide, which is the outline of my presentation. So the outline of my presentation is given here. So I'll give you a general background to the talk, and then I'll discuss about Leeds Alginate process, which we have developed, that is in my group at Leeds, to produce nanoparticles of functional materials. And using this particular method, I will focus on the synthesis and characterization of one of the compounds, that is pyrochlor compounds, holmium zirconate. And I will try to share with you some of the results that we have recently obtained from the applications point of view to solid oxide fuel cells. And finally, I will try to conclude with future directions of my research into this particular material. And of course, the acknowledgement goes without saying at the end of the presentation. So why are we doing this research? We are doing this research into fuel cell materials mainly because we think that fuel cell is the future of energy for energy production. Fuel cell will be the future in our opinion. I think this is not just my opinion. I think it is the opinion shared by a number of researchers across the world. And I think to some extent, these feelings that I have shared with you today about fuel cell were also echoed in some ways by the previous speaker in his talk, Dr. Bharat Kale, whom I have been fortunate to know for, I think, nearly 20 years now, if I'm right, 15 to 20 years. I have known Bharat Kale as a friend and colleague with whom I have interacted at various levels, like as a friend, colleague, as a collaborator, as a researcher, and many more. Why do we need to worry about this energy trilemma? Or what is the vision around this energy trilemma? So I think you may have heard this term, energy trilemma, or those who have not heard or hearing for the first time, I'll give you a bit of information about what is an energy trilemma. Now we know that whether it is manufacturing or transport or for domestic use, we need energy. Otherwise, without energy, you cannot light the bulb and everything will be dark. So we need energy, and not just we need energy, we need a secure supply of energy. So energy security is very, very important. It is right at the top of this particular triangle of energy trilemma. So providing energy security is very, very important. Now, it is not just important to provide energy security by any means. At the moment, we have been using fossil fuels to provide energy security for majority of the world. Now, fossil fuels are not going to last forever. And also, they are not environmentally friendly processes of producing energy because it produces a lot of carbon dioxide, and carbon dioxide, so burning fossil fuel to produce energy is definitely going to produce large amount of carbon dioxide. And carbon dioxide, as everybody knows, is a greenhouse gas, which causes global warming. And already the effects are seen in the Arctic, that the Arctic snow caps are melting, which is going to cause rise in the sea levels, and therefore it is a threat to the planet, its sole existence. It may not happen in our lifetime, but certainly, or even in our children's lifetime, but it will certainly have an impact over a few decades or maybe a century in time from now. And we need to act now to protect our precious planet and also provide a secure source of energy for foreseeable future, which is by not utilizing the fossil fuel, but by utilizing renewable energy sources. So if you want to provide energy security from alternate sources, then it has to be obviously affordable. So that is very important, because if it is not affordable, then I think it is not going to help very much. So it is necessary that you provide energy security at an affordable cost. So it is affordable to everybody across the globe. And also the technology that is going to be used for giving energy security will have to be produced by environmentally sustainable means. So how do you do this? It is not very easy question to answer. It is a very difficult question to answer at this time. But if we put policies in practice, or if you try to implement new policies, then certainly there is a way forward. So policies are very important. So that is why policy, energy policy is at the center of this triangle. So UK has put forward a policy document which says that by 2050, so it's an ambitious target, but there is a target set by UK. So by 2050, UK wants to be able to provide energy in a sustainable way with net zero carbon emission. So this is different from complete zero carbon emission, but what we are saying is that, or UK is saying is that we want to provide energy security at a net zero carbon emission. And because of that policy document that has come out, a lot of research has been spurred in the areas of materials technology or materials engineering, because materials are at the heart of the energy technology. You need new materials, you need efficient materials that can be used or developed into sustainable technology for providing energy security with net zero carbon emission. And I think fuel cells are part of that. Batteries are present, and fuel cells will be the future, which I think, if I remember correctly, even Bharat Kale in his presentation mentioned towards the end that fuel cells are, or hydrogen is hydrogen fuel cell particularly, are going to be the future of the fuel cell technology. And fuel cells are likely to be the way forward for providing energy security. Now, how do you produce hydrogen at an affordable rate or affordable cost? That is impossible to believe at the present moment, because the materials and the technology that is being used at the moment to produce hydrogen in order to power fuel cells to provide energy or electricity, it doesn't come at an affordable cost. It is a very expensive technology at the present moment. And also, it cannot be produced in quantities that are required for powering the world economies, because we are very power hungry at the moment. You know, and the power demand is going to increase in future as well. So we need an affordable source of production of hydrogen. So that is a very challenging, and that is what is driving research into hydrogen production processes. So I think that is why we are focusing our activities on solid oxide fuel cells. Now, going to the next slide, you can see, for example, if you consider today's automotive vehicles, Tesla has got a vehicle that is powered completely by batteries, which are essentially lithium ion batteries, and they are very expensive. You know, for example, a Tesla car with a basic model will cost you at least 70 to 80,000 pounds. It is environmentally friendly technology, but it will cost you as well quite a lot, because the batteries that are used are very expensive at the moment, or the materials to produce those kind of batteries are very expensive. However, Tesla and several other automotive companies, they have embarked upon lithium ion batteries as the way forward to meet the present demand for greener vehicles. If you look at the future, then future actually is in fuel cells, because fuel cells are the devices that can provide very high or the highest energy density at the moment. But one of the problem with fuel cells is low power density of the fuel cell. So this is a map of energy density versus power density. Lithium ion batteries sit somewhere in between the fuel cell and the electrolytic capacitors. So electrolytic capacitors, for example, or maybe supercapacitors, this is the future technology, electrolytic capacitors. So electrolytic capacitors have the highest power density, but lowest energy density, whereas fuel cells have lowest power density with the maximum energy density amongst the power technologies, power producing technologies that are available to us at the moment across the globe. So these are good for small electronic devices where you need sudden availability of large power. So small electronic devices, and therefore you need high power density. And if you need high surge in power, then you need electrolytic capacitors, or supercapacitors at the moment are currently being used. A good example is your camera flash. So I think that is a good example where it needs very high power, but it lasts only for a few seconds. So, or you need the power only for a few seconds, and then it starts charging up again. So supercapacitors are good for such devices, but they are not good. These kind of technologies are not at all applicable in automotive vehicles. So therefore, automotive vehicles at the present day and time rely quite heavily on lithium-ion batteries, such as Tesla's and Nissan Leaf, for example. So these are the two examples, good examples of automotive vehicles that are currently using lithium-ion batteries. However, lithium-ion batteries, because of their low energy density relative to fuel cells, they can only power domestic vehicles. They cannot power vehicles which have large mass. For example, railway trains. You cannot power railway train by lithium-ion battery, or you cannot move railway train by lithium-ion batteries. Or for example, HGVs, that is heavy goods vehicles, such as lorries and trucks, which go over long distance, you cannot power by lithium-ion batteries. Similarly, aeroplanes of the future, you cannot power by lithium-ion batteries. For example, hydrogen is one of the fuel that is used in propelling rockets to the space. You cannot propel a rocket to the space using lithium-ion batteries. It's impossible. So I think fuel cells have a great future in that sense, in providing high power, high energy density, but it comes at a cost. It comes at low power density, which means it has got more mass. So I think somehow, if we can address the question of mass or increase this power density and push this fuel cell somewhere to the right, at the same time keeping high energy density, then fuel cells have good future, provided we have an affordable source of hydrogen available to power the fuel cell. So there needs to be a significant amount of research that has to be done in pushing this fuel cell from this particular position onto the right-hand side, or maybe even in an ambitious program at a slope in that direction where you increase the energy density and also increase the power density at the same time. And the second thing is, so one is to push this in that direction. And the second thing is to make hydrogen available at an affordable cost. Now, this is possible by either photocatalysis, as Dr. Bharat Kale has mentioned, which is a green way of producing hydrogen, instead of steam reforming process, because steam reforming still produces quite a lot of carbon dioxide. So it's still not a green process. So photocatalysis is one of them. Even more, but the current problem with photocatalysis is the mass of hydrogen that is produced. That is still not sufficient, or the volume of hydrogen that is produced is still not sufficient by splitting water. One of the ways you can do this or achieve this is by splitting water using electrolysis. While electrolysis is a good concept of producing hydrogen, but it utilizes a lot of power. So again, you need to be able to combine the electrolysis process with, say, for example, solar cells, which can deliver power in a greener way to electrolyze water into hydrogen and oxygen, or using wind or tidal waves as the greener way of producing power to electrolyze water into hydrogen and oxygen. Okay, so that is a challenge. So again, that is the ambition of UK to be greener by 2050, more greener by 2050 than at the present moment, is driving these kind of technology or research into these kind of technologies at the forefront. So solar energy, tidal and wind energy, as well as solid oxide fuel cells. There is another aspect to this as well. So if fuel cell has to be a viable future technology, then lithium ion batteries would be sufficient for, or it would probably become more sort of obsolete if the fuel cell technology is going to move forward. So lithium ion batteries it has its own limitations. It has its own advantages and limitations. The main limitation is the availability of lithium. Lithium resources are not infinite. So I think that is the limitation that lithium ion batteries will have to face in future, whereas fuel cells would be able to cope with the available resources, which are the natural resources. For example, sunlight and hydrogen produced by splitting H2O, that is water, which is again an abundant source available at a very cheap cost. So sunlight and H2O are the two main sources which have to be utilized if fuel cell technology has to move forward into the future domain and serve us as the future energy technology. Okay, so why fuel cell technology is better than lithium ion batteries at the moment? This particular graph shows you a map of energy storage volume or system volume versus the range of the automotive vehicles that are using all these technologies at the moment in miles. So for example, if you look at lead acid battery, as Dr. Bharat Kale earlier also mentioned in his talk, that lead acid battery can power vehicles, or it is powering vehicles at the moment. However, lead acid batteries need their energy storage system volume is going to be very high if the vehicle has to be powered entirely on lead acid battery, that is without using fossil fuel, that is petrol or diesel. And if you power using lead acid battery, a vehicle with entirely, then you can see that you can power only, or it can run only up to 70 miles with a system volume, energy storage volume of about 700 liters. Lead is of course very heavy, and therefore you have to pay the cost of it, because that is the dead weight that you are going to be carrying if you have lead acid battery. And that is one of the reasons why lithium ion batteries have taken over as a future, near future, or modern day technology for powering the cars. So Tesla, for example, for the same 700 liters of volume, you can drive Tesla or Nissan Leaf for about 300 miles for the same volume of the energy storage. So battery volume, you can drive Tesla for about 300 to 325 miles. If you compare that with the fuel cell, you can see that, for example, the volume required by the fuel cell is roughly half that of battery. Okay, so lithium ion battery is roughly half for the same distance that you can travel in a car of the same weight. a domestic car. So there is that advantage here. That is the first advantage. Savings on the volume of energy storage system that would be required for driving the vehicle to the same distance compared to the lithium ion batteries, which are currently used in Tesla. The only problem here is availability of hydrogen. So if hydrogen is made available very easily, then the fuel cell technology is mature enough at the moment to take the leap into implementing this fuel cell technology into the cars and also into the heavy goods vehicle, which of course, lithium ion batteries, as I said before, is not suitable for heavy vehicles or railway trains or even submarines or ships, for example. So any heavy vehicle will have to be powered by fuel cell. In fact, some of the submarines are already powered by fuel cell in the military. Now, military can cope with the cost because they have unlimited budget or sort of unlimited budget from the governments, whereas domestic vehicles are dependent on the source of income of the individual. So you don't have the unlimited budget to power your car using fuel cell because of the current cost of hydrogen. Now, if you pressurize the hydrogen cylinder, which is within the car to drive the fuel cell to about 70 megapascals, then the volume required is even less for the same distance you drive using the fuel cell car. So this is the main advantage. So savings on the volume because of the high power density of fuel cell is very important here point to note. The second important point is the amount of time that is required to charge the batteries. At the moment, for example, if you look at Tesla or Nissan Leaf, to charge Tesla fully at a charging station, it takes about anywhere between, depending on the battery, it takes from anywhere between 4 hours to about 12 hours. So if you are doing a journey in excess of 325 miles, for example, and your battery has run out, then you will need to wait for at least 4 hours or even up to 12 hours. So you'll have to break the journey. Now that is not practically possible in every situation, because at the moment, if you look at the petrol or diesel powered cars, if you stop at the service station to fill up the car, it takes only 4 minutes for you to fill up a full tank of fuel and start your journey again. So again, that is the major disadvantage of lithium ion batteries. If you look at the fuel cell, on the other hand, it would take same amount of time as you require for filling in the gas in your pressurized tank, 3 to 4 minutes, similar to the petrol or diesel. And I think it applies same to even for CNG as well. I have seen CNG cars, several of them that are operating in India. And I think I have driven few times myself, those cars. And those cars take, again, the same amount of time as filling in diesel or petrol in your tank. So if you have a fuel cell driven car, then that is another advantage, which is a big advantage. So you don't have to break your journey for 4 hours to up to about 12 hours in order to fully charge your car and continue your journey. So again, it goes to show that fuel cell technology is there for the future, whereas lithium ion battery technology is for the present And maybe for the maybe few decades from now, say 30 to 40 years from now, after which perhaps battery technology may not be, or fuel cell technology may have overtaken battery technology if there is significant progress made in production of hydrogen on a large scale at an affordable cost to power the fuel cell. So I think these are the two main advantages, and I think fuel cell technology is there to last for a long time if the government policies are put in the right place to drive research into cheaper ways of producing hydrogen to power the fuel cells. Okay, so I think almost everybody would know in this audience what are fuel cells. Fuel cells essentially are, but I'll give you a brief introduction for those who are new to this. Fuel cell, they are basically electrochemical devices. There are two different types of fuel cells. One of them is a planar fuel cell, which is shown here on the top, and a tubular. So there are two main designs that are currently being researched into by researchers. And the fuel cell basically it has a cathode because it's an electrochemical device. It has a cathode, anode, and a separator of cathode and anode, which is a solid electrolyte. Now, solid electrolyte is a ion conducting membrane. So it could be a proton conductor, or it could be a oxide ion conductor. In this particular schematic diagram, all the three components of the cell are assembled together in almost a 1 millimeter thick flat surface. So you have cathode, anode, and an electrolyte sandwiched together between the manifolds on top and the bottom, which are basically carriers of oxygen and hydrogen. Similarly here, you have a similar structure, but in the form of a tube. So you have the oxygen or air going through the center, hollow tube, and you have the fuel on the outside of the structure. And you have the electrolyte, which is in the middle, which is essentially an oxide ion conductor or a proton conductor. So this is a schematic diagram of the solid oxide fuel cell, how it works. So you have the hydrogen coming at the anode, forming water, and the free energy change for the formation of H2O from hydrogen and oxygen, which are traveling from the cathode after being reduced at the interface through the electrolyte across and combining with hydrogen to form H2O. So the free energy change basically is, it will give you the theoretical voltage drop across the electrodes, which will then be converted into power when you have load connected to the cell. And the electrons flows from, of course, the anode to the cathode, and the circuit completes. In the external circuit, the electrons flow from the cathode to the anode, and the circuit completes. Now, one of the problem in achieving the theoretical voltage drop, you don't get theoretical voltage from the fuel cell, mainly because there are places where the voltage drop occurs. One of them is at this interface, which is the anode and the electrolyte interface. Cathode and the electrolyte interface. And the electrolyte itself has its own resistivity. And the interface at the anode and the electrolyte. So high surface area anodes and cathodes have been used in order to provide greater triple phase boundary in order to facilitate the electron exchange that is taking place at the interface, the two different interfaces at the cathode and the anode. The biggest drop occurs through the electrolyte, and therefore the thinner the electrolyte, the better it is. So if you have thinner electrolyte, there'll be a lesser voltage drop. If you have a thicker electrolyte, you will have a larger voltage drop across the electrolyte. So that is one of the areas of research that is taking place. And for all these, so to produce high surface area anodes and cathodes, or to produce a thinner electrolyte to sandwich between the two electrodes, there is a greater need for developing nanomaterials of all these components in a solid oxide fuel cell. Presently, the solid oxide fuel cell uses oxide ion conductor, which is yttria stabilized zirconia, and also gadolinium oxide doped ceria as the solid electrolyte. There have been some research done into bismuth oxide based electrolyte, which has much higher conductivity than yttria stabilized zirconia or gadolinium oxide doped ceria. However, bismuth oxide based electrolytes are quite unstable when it comes to low oxygen potentials that are present at the anode of a solid oxide fuel cell. So there is a problem there. So much of the research has gone in to use bismuth oxide as the electrolyte at the interface of the at this interface, which is the cathode interface, where oxygen potential is higher, and you have a graded electrolyte being used, where it goes from bismuth oxide rich to yttria or gadolinium doped ceria rich electrolyte materials. So with this background, I would go on to the next slide, which is different processes that are used for making these nanoparticles or nanopowders. Again, the challenge here is scaling up. Can you scale up various processes for producing high quality nanopowders of components that are required in a solid oxide fuel cell? So sol-gel process was one of the early processes using organic precursors, but they are very expensive. Organic precursors are very, very expensive. And this particular process generally is useful only at the research stage when you have to prove a point or prove a concept. When it comes to large scale, I think this process fails miserably to deliver the required economic production of large scale powders that are required. Co-precipitation is another process. I won't go into details of these processes because I think everybody would be perhaps familiar with the processes as well, how they work. So I won't go into details about that, but co-precipitation is another process which is used for making nanopowders, but again, it needs higher calcination temperatures and to form a single phase. during that process, there will be crystal growth, and you lose the effect of producing efficiently nanopowders. Again, hydrothermal synthesis is been tried, which is also a lab-based, more sort of a lab-based process rather than an industrial scale process. It is difficult to scale it up to produce large scale powders using hydrothermal process. Spray pyrolysis and flame pyrolysis are interesting because they can be used actually to produce large scale nanopowders. Well, not nanopowders, but micron size powders. To produce nanopowders using flame pyrolysis or spray pyrolysis is again difficult because of the problems with containment of the particles. So there are problems with the containment of the particles because of the nano size of the particles that are produced or that could be produced potentially from spray or flame pyrolysis process if you try to produce them at those scales. Combustion synthesis again is an interesting. So both, I think I'll combine these two, combustion and microwave synthesis, because the problems faced in combustion and microwave synthesis are also similar. They are economical processes and could be scaled up. However, the main problem with these techniques is thermal runaway. So in combustion synthesis or microwave synthesis, there is always a possibility of thermal runaway, and that can lead to wide range of particles, that is particle sizes of the material that you produce using these, or sometimes even inhomogeneous materials can be produced, and that is not good for the application if you want to apply these materials in technologies. Organometallic vapor phase synthesis is again similar to sol gel. Organometallic vapors are, or organometallic compounds, which are used again as precursors here in sol gel process. They are very expensive, and therefore, even though this technique has potential of producing very fine uniform single phase nanopowders, it is quite expensive to produce. So with these drawbacks in different kind of limitations of various techniques, we looked at different techniques and we stumbled upon this particular technique, which is, we named it as Leeds alginate process. So this is a very simple process where you, it's an ion exchange process. So you have the polymer, which is the alginic acid or sodium alginate, which is basically a polysaccharide. And it has got carboxylic acid groups in it. And those carboxylic acid groups are very active and they can be easily ion exchanged with various metal ions from the solution. That is from the aqueous solution. So these are aqueous precursors, unlike organic precursors or organometallic precursors used in these two methods. So we did quite a lot of research in this area. We've been working in this area for last almost 4 or 5 years now, or maybe more. And we have produced a wide range of compositions of various functional materials for various applications, say it for sensors or fuel cell or batteries. So why this particular process is attractive or has attracted us? The main reason is that it's a cheap material. Alginate, sodium alginate, or alginic acid is a very, very cheap material. And we have abundant resources available to us because sodium alginate is extracted from seaweeds. And if you look at the amount of or the area covered by sea and oceans across the globe, we have a huge amount of area that is available to us to harvest seaweeds. And that is one of the reasons why sodium alginate is cheaper, because there is abundant resources available, and it is very easy to purify or extract sodium alginate from the seaweeds. Sodium alginate already is a multi-billion-dollar industry. So for example, this figure was taken a few years ago, I think, but this would have increased perhaps. But even if you look at the figure from a few years ago, it used to be a $6 billion US dollar industry in those say few years ago, which could have probably grown by another $1 billion now, mainly used in food industry, pharmaceuticals, for drug delivery, and in cosmetics. So this is mainly used in these three industries: food, pharmaceutical, and cosmetics. And it is very highly affordable as well, because it is produced at a very, very cheap rate. Added to that, it has a great advantage of ion exchanging ability to ion exchange with cations, and therefore you can easily ion exchange with different cations. For example, in this case, it is schematically shown for calcium. So if you have a divalent cation, then the linear chain polymer assembles itself into a particle, and that can be easily dried and calcined and converted into functional nanomaterials. It's interesting to note that in most cases, the calcination temperature that we have found for various materials is always around 400 to 500 degrees Celsius. Now, what are the merits of using this particular method? The merits are that it produces consistently high surface area nanopowders, typically in the range of 10 nanometer or somewhere around there, even after calcining at such high temperatures, 500 degrees Celsius. The nanopowders that are produced are consistently in the range of 10 nanometer, 10 to 20 nanometer. It has the lower temperature of synthesis, and therefore restricts, or one of the reasons to restrict grain growth. It always produces with enhanced homogeneity, so you don't need further purification to increase the homogeneity or purity of the material. So as it is, once you calcine, you get consistently high purity material. Easy to control composition during the synthesis process. The ease of component fabrication for mass production. So it is easy because it's scalable. This particular method is scalable. It is relatively cheaper to produce components out of the powders on a mass scale. The sintering temperatures are lower because every material in a fuel cell needs to be sintered so that it is dense. And because of the nano size of the or high surface area of the powders that are produced, it is able to sinter at much lower temperatures compared to conventional powders. It is less energy intensive process or processing steps, and it is inexpensive precursors. So the precursors are inexpensive. You don't need organometallic precursors. And also the alginate that is used is relatively inexpensive. The main problems are, so these are some of the demerits which we could think. One needs to always worry about toxicity of nanopowders. So containment of nanopowders is very important during the scaled up process. There are currently some teething problems of scaling up. So it's a basically chemical engineering problem. And we are looking into developing process to scale up a prototype lab, scale up process where we are trying to produce kilogram scales of nanopowders using this particular method. So the simplicity of this method. So this method is relatively simple. It has low carbon footprint. Probably, I would say carbon neutral, but I think it is stretching stretching it a bit too far at the moment because we have not worked out how much or the carbon balance basically. However, we are pretty sure that it is having a lower carbon footprint than most of the other processes that I have mentioned before. It is environmentally friendly, and therefore it has got greater sustainability for the future. These two problems need still to be addressed: the cost reduction and scale up. So once you are able to scale up the process, obviously there will be a corresponding effect of cost reduction for producing these materials. So I think I will now focus on the pyrochlore, that is holmium zirconate that we have looked at and how we have applied this technique to produce these materials, this particular material. So what we have done is, this is a simple schematic diagram. So we have the metal nitrates or metal salts that are mixed in appropriate ratios to form the compound. And then you have the sodium alginate, which is which is converted in the form of gel. So the powder is converted into gel. And once you bring the alginate in contact with metal ions in the solution, it instantaneously converts into beads, and these beads are then dried and calcined to produce nanoparticles. This is a very simple schematic diagram of how we produce nanoparticles. So this is an experiment that we did with, I think, quite a while ago. This was the initial stages of trying to prove the technique, which was done in 2012. We published some of our work in this particular paper in 2012 on nickel oxide. So we produced nickel oxide. Now, nickel oxide, again, we wanted to investigate this because it has applications in solid oxide fuel cell as a component of anode material. So we looked at nickel oxide, and what you see here is the nickel oxide, nickel ion exchange beads here with sodium alginate, and you have the dried beads, which are very green, which is a typical color of nickel. So you can see that they're very nice green color beads, dried beads. We also did some examination of the internal structure of the beads, the dried beads. So these are the dried beads as you see here, these ones. And what you see is an interesting. So we did X-ray microtomography of the alginate dried beads, nickel alginate, and what you see is a very porous structure. So you can see that there is a very porous structure. So all these veins are the locations where you have metal ions that are present. And in between these veins, you have the empty space in the dried beads when the water is gone. So what you see here is that because these veins are widely separated from each other, during the calcination, that's what we believe, that even though we have to calcine these beads at about 500 degrees Celsius, because of the lack of diffusion path between these veins due to the presence of void, it is not possible for the grains to grow. And hence, it consistently produces nanoparticles. Instead of allowing the particles to grow, and that's what happens during the co-precipitated materials, because there is no empty space, and therefore the particles are in contact during the calcination process in the co-precipitated material, and therefore it is hard to get nanopowders consistently. Now, this particular work we presented, published in one of our papers in RSC Advances several years ago. In the same paper, we also published the calcine bead. So this was the dried beads, and you can see that even after calcination, the structure is retained. The overall structure of the calcine beads is still retained, and you can see that the empty spaces are still there, which prevents the particles to grow, but at the same time allows the particles to react together to convert into the product phase, which is a single phase product. Now, we applied the same technique to synthesize holmium zirconate. The reason why we decided to move to a slightly unconventional material as an electrolyte for solid oxide fuel cell is because of the interesting properties that the structural properties that pyrochlore phase or A2B207 type of phase presents. So you can see that these are the rare earth, this is a rare earth series, lanthanum to lutetium. So this is a complete rare earth series, and this particular, so at the bottom scale, you have the ionic radius of lanthanide. So you can see that there is a critical ionic radii of lanthanide at which the structure converts from fluorite to pyrochlore. Now, this is typically around 1.46 to 1.48, around that. So at that, so you can see that this is the ratio of lanthanide, radius ratio of lanthanide ion to hafnium in this case. But again, the same thing applies to zirconium as well. So if you plot the same, because we have worked on both materials. So if you plot the this particular map for lanthanide ionic radius to zirconium ionic radius, that ratio, then again around 1.46 to 1.48, you see that fluorite transforms into pyrochlore and vice versa. So pyrochlore transforms into fluorite around that radius ratio. So this is an interesting, structural property, and as a result, this particular material is quite flexible in number of ways. For example, in ionic conductivity, or in accommodating ions of different sizes in the structure. And this has been very elegantly shown recently by a paper which was published in Nature in 2016. So that in that paper, which it is very elegantly shown why this material is interesting for various applications, such as for immobilizing radioactive nuclei, or as fast ion conductors, because fluorite phase has oxygen ion vacancies, which can be exploited for enhancing the oxygen ion conductivity by manipulating the composition of this material. And also for thermal barrier coatings, for example, fluorite are good ionic conductors, whereas pyrochlore are poor ionic conductors, and therefore the same material with the same composition can be used as thermal barrier coating material as well, and so on. So people are trying to explore some of the properties at the moment. And there's another paper here, interesting paper, which was published in Journal of Alloys and Compounds on the conducting properties, ion conducting properties of this material, pyrochlore material in 2016. So we looked at holmium zirconate, which was prepared from by the process that I mentioned before. And again, I mentioned before as well that around 500 Celsius, you can see that this is the last weight loss that we get on TGA DSC data, where you can see that there's a complete transformation of the initial product or the precursor into the fully crystalline holmium zirconate nanoparticles. And this particular work was published recently by us in Thermochemica Acta, which is part of one of my students, PhD students' work. We also did the high temperature X-ray diffraction because to support this, because this is a dynamic technique. DSC TGA is a dynamic technique. So instead of just looking at the X-ray diffraction pattern at the end point of calcination, we looked at, we did some temperature programmed study of X-ray diffraction pattern from room temperature up to about 1000 degrees Celsius. And we recorded the X-ray diffraction pattern in situ in a controlled environment. And what we find is that, again, this corroborates very well with the data that we got here in this particular diagram, DSC TGA diagram, that the nanoparticles of fluoride structure, so this holmium zirconate is a fluoride structure, has a fluoride structure. You can see that the peaks start appearing almost at around 400 degrees Celsius, 400 to 450 degrees Celsius. And at 500, you can see that they are very clearly visible, the peaks that are very clearly visible. The peaks are very broad because of the nature of the particle itself. So because they are very tiny particles, nanoparticles, you expect X-ray diffraction peak to be broad. But as the temperature increases, you can see that the peaks get sharper and sharper. And of course, we did some retwell refinement as well to prove that there are no impurity phases. So this particular composition is a fully crystalline phase produced at about 500 degrees Celsius in the form of nanoparticles. So this is a high resolution transmission electron micrograph of the nanoparticles, and you can see that they can be fully indexed with the pattern, X-ray diffraction pattern of fluoride structure. And if you look at the marker here, that is a 5 nanometer marker, and you can see that these particles are typically about 10 nanometer in 10 to 15 nanometer in size. We also did the EDX analysis in TEM. So you can see that this is the ratio of holmium to zirconium to hafnium. And you can see that it is perfectly in agreement with the stoichiometry of holmium zirconate. Now, once you have the nanopowders, we did some investigation on sintering of the material as well. And what we found is that the material sinters to almost full density which is 96% of theoretical density using a two-step sintering process, whereas with the conventional sintering process, it attains only about 93% of density. Now, density of the electrolyte is very important in a solid oxide fuel cell, because if your material is not dense, then there is always a possibility of mass transfer across the electrolyte. And if there is a mass transfer across the electrolyte, then you always lose the voltage, because that much of mass of the gases is not available when it crosses over from anode to the cathode or cathode to the anode for the voltage or the chemical reaction. Because what is a fuel cell? Fuel cell basically converts chemical energy into electrical energy. So if your availability of the gas is low compared to what you flow in at the anode, then you lose that power, and therefore the density of the electrolyte is very important. And the limit of how thin you can have the electrolyte is again a function of density. So if you have, if you want thinner electrolyte, then you need to have high density. If you have lower density, then you need to have thicker electrolyte so that you avoid mass transfer across the electrolyte and loss of voltage as a result. So it is very important that you need to have a high density. So two-step sintering process gives us very high density, almost 96% of the theoretical density of the solid electrolyte. Whereas the normal sintering gives only about 93%. So these are some of the microstructures of, so these are the microstructures of from A to E are the microstructures, SEM microstructures of the dense material that we produced by sintering at different temperatures, starting from 1100 to 1500. And then this is at 1300 degrees Celsius. So you can see that by two-step sintering. You can see that even at 1300 by two-step sintering, the density is extremely high. Then we did the impedance spectroscopy, which the results of these are published recently in Ceramics International. So we did some impedance spectroscopy to calculate the conductivity. And these are the, because that is one of the parameters that you need to measure to assess the potential of the material as a solid electrolyte. So what you see here is nothing very unusual. So it's a basically standard plot, Arrhenius plot, which gives you the activation energy and the conductivity from the impedance spectra. So these impedance spectra are measured over a range of frequency as a function of temperature to arrive at this data. Now, the interesting thing is, or the uninteresting thing is, that it is not very unusual. So we haven't got the conductivity even anywhere close to yttria stabilized zirconia. So what can we conclude from this? So what we can conclude is that this material is no good for using as the, or in its current form, no good for using it as the solid electrolyte. The only advantage of this material is that it is much more stable thermodynamically compared to, say, materials such as ceria gadolinium, and almost with similar stability, thermodynamic stability as yttria stabilized zirconia. So the challenge here is for us in the future is how to improve this conductivity to a better value that is then made suitable for fuel cell application. So this is actually the comparison of ionic conductivity of two-step sintering process compared to the single-step sintering process. So again, two-step is about half an order of magnitude higher than the single-step, this conventional sintering process. Okay, so the question is, how do we improve this ionic conductivity of A2B207, particularly the holmium zirconate that we have got? So holmium, if you look at the ionic radius of holmium 3+, if you look at the ionic radius of holmium 3+, it sits somewhere here. Okay. Now, there was a paper that was published in, I think, early 90s by a Japanese group in solid state ionics. And what they showed is very interesting. And that is what is quite promising about this material. So what you see is that holmium zirconate that we prepared sits somewhere here. And what it shows is that it has got conductivity that is not very promising at the moment. So what this particular graph shows, that is conductivity as a function of ionic radius. So what we see here is that when you go close to the fluorite pyrochlore phase boundary, which is structural phase boundary, which is shown here by dotted line, the conductivity suddenly shows an anomaly. Okay, so it suddenly increases quite rapidly around the fluorite pyrochlore phase boundary. And then it again, as you go away from it, it starts dropping down in the pyrochlore phase. So this is pyrochlore domain. This is fluorite domain. So what we intend to do is, in the future, to increase this ionic conductivity, we intend to, or the logical way is to dope it with gadolinium or europium. So if you dope it with gadolinium or europium in selected amounts, and then look at the conducting properties of the solid solution. Now we know that it does form solid solution, a continuous series of solid solution. So whether it is in the fluorite phase or in the pyrochlore phase, so it forms a continuous series of solid solution. And what we expect, or the research is already in progress in my lab, where we are looking at doping holmium with gadolinium and europium and analyzing the results of conductivity. And if this is true, if this graph is a true representation of fluorite and pyrochlore phase of the rare earth systems, whether it is zirconate or hafnate, then there is a good likelihood that this material would surpass the ionic conductivity of yttria stabilized zirconia and will be very close to ceria gadolinia type of electrolyte. Now, what is the advantage? If this material is close to, or is brought close to ceria gadolinia system, then obviously this material will be thermodynamically more stable in the oxygen potential gradients that are existing in the solid oxide fuel cell between anode and the cathode. And therefore, there is a less likelihood of any reduction taking place in the elements of the electrolyte, which normally tends to happen in ceria gadolinia system. Because in ceria gadolinia system, cerium is well known to exhibit cerium 3+ and cerium 4+ state. Ideally, you want cerium in 4+ state, but cerium usually tends to go into cerium 3+ at the anode electrode or close to the anode electrode because of the lower oxygen potentials present at the anode of the solid oxide fuel cell. So that is our future path of research in my lab on this particular system. holmium zirconate and holmium hafnate. So with that, I would like to conclude with few conclusions which are shown here. What we can conclude at this stage is the scale up of the process is one of the main challenge in developing this particular process technology. Scaling up of the process technology is a multidisciplinary engineering problem, which I think I have alluded to that before. And a successful, we believe that successful scaling up of the process will lead to reduction in the cost of nanopowder production, not only for materials that are useful in solid oxide fuel cell, but in other technologies as well. Because scaling up is important if you want to apply a material in any particular technology, whether it is batteries, fuel cell, or catalyst applications for various reactions. It is important that the materials are able to scale up in a sustainable way and are produced in a scaled up process in a sustainable way in an energy efficient process. So if this, so the next challenge for us is to scale up this process, alginate process. And if that is possible, then we could have significant energy savings, and not just energy savings, but the cost reduction as well for the production of nanopowders for applications in components and devices for various technologies. And of course, finally, it will make the ceramic nanopowders available at an affordable cost to other technologies which are currently not being able to use nanopowders because of the unaffordable cost or formidable cost of the ceramic powders that are required in various technological applications. So it'll open up new areas for nanopowder applications as well. Without acknowledging the financial support, it is certainly not possible to conclude my talk. So I would like to acknowledge the support received from Indonesian government in this particular project, the Commonwealth Council of UK, and all these people who have worked on this particular project. And last but not the least, to all the audience who have patiently listened to my talk in this webinar. So I thank you all from the bottom of my heart for listening patiently and keeping attention throughout the talk. And I'll be happy to answer any questions if there are related to this topic. Finally, I would like to leave you with this particular image of the Great Hall of University of Leeds, which is one of the oldest buildings of University of Leeds. And this is where we hold all our degree ceremonies. So all the degree ceremonies, so students are basically honored in this particular hall when they are presented with their degree certificates and any awards that they receive during their course of study at Leeds University. So thank you very much for your attention, and I'll be happy to answer the question. Thank you.
Thank you so much, sir. Participants are requested to ask their questions. Sir, would you please stop sharing your screen?
Yeah.
Okay, thank you so much, sir. So we will take.
I hope it was visible and audible clearly.
Yeah, it was. It was.
Thank you. Thank you for the, sorry for the initial hiccups.
Okay.
Hello, sir. Dr.
Hello.
Sangle.
Hello.
Good audible and visible.
Thank you.
One question is here. When we study the low temperature magnetization
Right.
of the pyrochlore,
Right.
so what is the benefit of that?
You could perhaps, I mean, depending on the quality of the data that you get, they could be useful in as a multiferroic materials for electronic devices or spintronic devices. You could use them even in sensors, for example, or for biomedical sensors. There are applications of magnetic materials in drug delivery as well. So you can use them for efficient drug delivery or targeted drug delivery. So there are applications. The important point here is that particularly for biomedical applications is that the toxicity of these materials have to be very clearly understood before they are used as in applications, in biomedical applications such as drug delivery or biosensors, particularly the not the in vitro biosensors, but for in vivo biosensors.
Yeah, good. Sir, instead of gadolinium, holmium, and europium, when we dope the another rare earth?
Another rare earth, depends on what you want to achieve by doping. We would like to dope with europium or gadolinium because we want to essentially increase the ionic conductivity. So that is the main reason for us doping with gadolinium or europium. I mean, gadolinium is an interesting prospect because holmium is very expensive material. So if you dope with gadolinium, you are thereby reducing the amount of holmium that is used. And therefore, it could perhaps become more cost effective. So that's another advantage. Because ultimately what you want is, I mean, research is good. All researches are good. But I think research, the main aim of research, as I see it, is to benefit mankind. And how can the research benefit mankind? The research can benefit mankind only if it is utilized by mankind. And the only way you can increase the utility value of the technology is by making it more affordable to the mankind, because everybody has different affordability. Not everybody doesn't have same affordability. So if you make it affordable for a common man, a technology, then of course, that should be the driving force for the research direction.
When we heated the material greater than 500, the structure it changes to pyrochlore to spinel or peroxide?
It could change depending on the temperature. If you look at that map that I showed you for pyrochlore to fluoride transformation, it is temperature dependent. So you can control the structure by either using an appropriate dopant so that you change the radius ratio of the average radius ratio of the trivalent cation to tetravalent cation, or by temperature. Yes. So there are two ways of changing the structure. So either by temperature or by changing the radius ratio.
Thank you, sir. Thank you.
Thank you, sir. The last question that we're having here.
Right.
The question is asked by Mr. Desai. Is hydrothermal process feasible in alginate synthesis process of nanopowder?
Alginate process, I doubt about application of hydrothermal synthesis for alginate process, but I mean, this is something which we haven't thought. So it's a good question. And obviously, you know, because we have not done that or we have not studied that particular line of thought, I cannot really confidently say whether it is, you know, it is possible to use hydrothermal or not. But again, the problem we have not, the reason why we have not thought about hydrothermal is because of its limitations itself, because it cannot be, it is not easy to scale it up. That's the main problem. So that's why we did not think about you know, using hydrothermal. But yes, I mean, go ahead. You know, if you want to try alginate process in hydrothermal conditions, I think you can try and see what happens. That's what is research about. You know.
Yes.
Thank you so much, sir. Thank you so much for your beautiful presentation in wonderful English.
Thank you.
And the crux of what you have just presented is without sustainable development of sustainable energy, there could not be sustainable development in future. And
that is
renewable
true.
energy, renewable energy is future.
That is true. Absolutely. Absolutely. And the important point is, like Dr. Bharat Kale also said, you know, hydrogen is the future. You know, hydrogen is the future. But how can you make hydrogen future if you cannot produce it by, you know, affordable process? So again, the challenge here is hydrogen. Yes, hydrogen is the future, but how can you produce it in affordable way is the biggest challenge that everybody needs to address.
Yeah. Thank you so much, sir, for your beautiful presentation. Thank you so much.
Thank you very much for your attention. Thank you. And I'm very honored to be, you know, part of this particular webinar. So thank you very much. Although it was a last minute, you know, call, but I hope you have enjoyed as much as I have, you know, taking part in this.
Sir, we are very much humbled by your words. Thank you so much, sir. Now moving towards the concluding part of this international webinar, may I now request Mr. Shahaji Mane, Head Department of Chemistry, Professor Dr. N. D. Patil Mahavidyalaya, Malkapur, to propose a vote of thanks of this web seminar. Mane, sir, over to you.
Thank you. Hello, I am audible?
Yes, yes, sir. Please go ahead, sir.
Hello, good evening. Myself, Mr. Shahaji Mane, Vice Principal and Head of Department, N. D. Patil Mahavidyalaya, Malkapur. French philosopher Voltaire says that appreciation is a wonderful thing. It makes what is excellent in others belong to us as well. With this thought, I am here to propose vote of thanks of this web seminar. I express my deep sense of gratitude towards Dr. Bharat Kale, the speaker of the first session, for his presentation of nanostructure and their applications. Sir, your ideas have already really enlightened our participant with your insightful observation. I sincerely thank Dr. Girish Kaiser, speaker of the second session, who has wonderfully presented his view of effect of crystal structure on conductivity of A2B2O7 compound. Sir, I appreciate that you shared your valuable time with us. I am thankful to our beloved principal and convener of this web seminar, Dr. Sunil Helkar, who always motivates us to conduct activities. I also thank organizing secretary, Dr. Mohan Sangle, and coordinator, Dr. Pande, and other organizing committee members who ensured smooth organization of the events. I thank all teaching and non-teaching staff that is actively involved in making the web seminar successful. I give a big thank you to Mr. Sanjit Desai, who gave his technical support to make this web seminar successful. And last but not least, you all participants I extend my heartfelt gratitude for showing love and support to the web seminar. Thank you so much for being with us. With this, I declare that this web seminar is over. Thank you once again. Thank you.
Okay, thank you so much. Participants are requested to go through the link that we have given in chat box. It happens that due to huge traffic, sometimes you're not able to go through that link. So keep trying, and soon you will receive your certificate through that feedback form. Once again, I thank all the participants, speakers, and everyone. And I declare that this web seminar is over. Thank you so much.
Thank you.
Thank you.
Girish sir,
Yes.
we will meet again after your time in future.
Sure, definitely. I mean, you just send me an email and we can organize that.
Yes, sir. Yes, sir. I am very much thankful our college, all members, and very informative, good, silent, very special pronunciations and good lecture.
Thank you very much. I really appreciate your kind words, definitely.
Really.
It was nice to see you all as well. You know, it was great. I mean, I have very close links with, as I said, with Bharat, but not just Bharat. I have close links with Pune as well, because I was born in Pune basically, and I belong to Pune. So all my families are in Pune as well. So it's a very close connection with Pune, and of course with Maharashtra as well.
I'm living in Shirdi, Sai Baba Shirdi.
Yes, I know. I mean, it is very close to Ahmednagar. I think I mentioned about Ahmednagar to you yesterday.
Yes.
So I know about Shirdi as well. Yes, very nice.
Bharat Kale sir and myself is the family relation.
Oh, okay. I mean, I'm not related to Bharat Kale, although we share the surname.
Yeah. But I am living in Shirdi.
Right.
When will you come in future?
Sure, definitely.
Please come, call, communicate.
Yes, definitely.
WhatsApp.
Yeah, I mean, this is the beginning. You know, this is the beginning. Now we know each other through this webinar. I think I'll be happy to answer anything what you want to ask me. Just drop an email or yeah, I mean, you have my contact number as well. So
thank you, Girish, for getting for the time.
Thank you very much. Thank you very much for inviting as well. Namaste. Namaskar. Okay. Yeah.
Bharat sir.
Sangre. ठीक है ना?
एक नंबर. Thank you. साहेब काय म्हणता आमचे येलकर साहेब बोला ना. काळे सर पहिलंच तुम्ही आडनाव घेतलं. साहेबांचं आडनाव आता येलकर झालेलं.
आलो.
येडकर.
हा ठेव.
बरोबर, मला नाही माहिती.
साहेब बोला. हॅलो साहेब बोला. गाडी बंद दिसत नाही. एकंदरीत छान झालं सगळं.
छान झालं ना? चला, काय प्रॉब्लेम नाही. चला.
उत्तम, छान आहे, उत्तम झालं.
गिरीश, तुमच्यामुळे शोभा आली. तुम्ही
अरे असं कसं रे? आय मीन, माझ्यामुळे शोभा कशाची? सर्वांच्या मुळे शोभा आहे. माझ्यामुळे एकट्यामुळे मी एकटा काय करणार? जर ऑडियन्स नसतील तर मी एकटा काय करणार भाषण देऊन? ऑडियन्स आर मोर इम्पॉर्टंट दॅन द स्पीकर.
हॅलो सर.
हा बोला साहेब.
बोला सर.
आपला हा वेबिनार अतिशय उत्तम झाला. आणि सरांची लँग्वेज आहे ना इतकी सिंपल आणि लुसिड आहे की सायन्स मध्ये एवढं मोठं काम असताना सरांची जी लँग्वेज भाषा जी आहे ना सर्वांना समजणारी आणि अतिशय उत्तम आहे.
थँक्यू व्हेरी मच.
विशेष करून परदेशातल्या आपल्या भारतीय माणसाचा बोलण्याचा टोन हा वेगळाच असतो. मी पुण्यामध्ये 8 वर्षे राहिलो. पुणे विद्यापीठातच मी डॉक्टरेट केली. पण मला तुमचा हा साधेपणा फार भावला आणि तुमचे विषय तुम्ही संथपणानं आणि फार छान दोघांनी मांडला.
अप्लाइड वर्किंग दोन्ही अप्लाइड.
आता भविष्य काळामध्ये हे कोविडची नॉर्मलशी आल्यानंतर जेव्हा तुम्ही भारतात याल त्यावेळेला कोल्हापूरमध्ये आमच्या विभागाला भेट द्या. आम्ही तुम्हाला त्या भागामध्ये नेऊन तिथलं हिस्टॉरिकल प्लेस वगैरे सर्व दाखवूया.
नक्की नक्की येणार.
आम्हाला आनंद वाटेल.
त्याच निमित्ताने कोल्हापूर मध्ये पण जाता येईल. कोल्हापूरला पण जाता येईल.
अगदी अगदी. हो.
नाही तर सहसा म्हणजे माझं कसं आहे की कोल्हापूर हे सगळं म्हणजे लांब पडतं माझ्या नॉर्मल रूट पेक्षा. माझा नॉर्मल रूट आहे मुंबई, पुणे आणि बँगलोर एवढाच आहे फक्त.
मग कोल्हापूर हे ऑन द वे बँगलोरलाच आहे. NH4 वर आहे.
बर.
आणि हा सह्याद्रीचा पूर्वेच्या उतारावर कोल्हापूर शहर आहे. देवस्थान आहेत, मोठे किल्ले आहेत आणि ऐतिहासिक हा असा परिसर आहे.
नाही मला इतिहास म्हणजे खूपच आवडतो. म्हणजे कुठलाही इतिहास असू दे. म्हणजे भारताचाच असायला पाहिजे असं नाहीये. पण कुठलाही इतिहास म्हणजे आय एम व्हेरी आय एन्जॉय लर्निंग मोर फ्रॉम द हिस्ट्री.
मग आपली आवड आम्ही पूर्ण करू. तुम्ही जेव्हा भारतात याल त्यावेळेला आपण भेटूया जरूर.
नक्की नक्की.
एक गोष्ट सांगायची. हॅलो. आपले भारत काळे सर हे रयतचे विद्यार्थी आहे बोरावके कॉलेजचे.
श्रीरामपूरचे. वा वा वा. छान छान.
आपल्या रयत मध्ये त्यांचं खूप योगदान आहे. म्हणजे आतापर्यंत ज्या ठिकाणी रयतचे नॅशनल इंटरनॅशनल कॉन्फरन्स झाले त्यामध्ये ज्या काही इनोव्हेटिव्ह आयडिया त्यांनी आपल्याला खूप दिलेल्या आहे. आणि भविष्य काळात आता तुमच्या कानावर घालून ठेवतो रयतच्या दृष्टीनं. म्हणजे एक सायंटिस्ट माणसं आपल्याकडे आले तर आपली प्रगती होईल.
निश्चित. अगदी अगदी निश्चित होईल. आपण दोघांनाही बोलूया कॉलेजवर. त्यांनाही छान वाटेल. आपल्यालाही त्यांच्याशी समोरासमोर भेटता येईल.
नक्की.
अच्छा सर. पुन्हा आपलं एक वेळ मी आभार मानतो.
थँक्यू व्हेरी मच. नमस्कार.
अच्छा सर. अच्छा.
ओके. थँक्यू.
ओके. आपण थांबूया आता सर.